好，我们马上开始哦。我们先来看一个小东西。
Definitely a lot of human-like environment because essentially so now with the hardware and also demo floor, but however object there are open methods of viable path towards mainly wise it's actually hard to high degree and also very hard involves
这个是第一个阶段哦。第一个阶段是人抓着机器的手背直接去做。那你的机械手背的 state 状态，真实的状态是借由上面的各种sensor直接拉回来的哦。
Like there's not, however, the terror of divisive effort always operate, learn provide them. However, results require also it's hard to say how do we robots way a very big childhood as the underlying learn. Let's check from science study decades where is that this young baby ability how the adults task in, and know that it's so natural that there's demonstration broken task single hand, but also interaction is definitely not natural. By this study together, anyone recording or because devices involved.
这个是在1年前发的论文啊，这是在1年前发的论文，说1年多以前发的论文。那在1年前所发表的这个演说哦。
However, challenge first in that action also so that challenge is that the look at how so that understand how the hands are one is object standing everything are being plated.
我们看这个目的哈，其实有一个就是我们怎么把人的行为跟那个机器的行为做 mapping， 其实是一个还蛮重要的动作。我们如果人的骨头就是你的上背就是2只、3只啦，其实是3只，就是前背是2只肱骨，它是交叉的，上背是1只比较大的、比较粗的。那你用这3只骨头怎么运作？那你要把那个自由度转成机器人上面，转成那个 robot roll out 这件事情。其实我今天想要给大家看一下的是这件事情。其实我先问一下，大家知道我现在在干嘛吗？就是语言模型本来就可以做到很好的主词跟受词 name entity recognition。那从去年的那个时候到今天更是可怕，这个已经是到很可怕的地步。那你今天在做这件事情的时候，其实是在定义主词跟受词。如果是你要做人要去做什么动作，那很显然是人对什么动物、什么物体做什么事情，所以那个物体辨识出来，用 AI 辨识出来。那如果你的 AI 又有一个那个什么 segment 的功能，你就可以把这个物体特别分出来，连续的分出来做 segment。人也可以。这个我觉得是在我们说 data 有分成4层，最上面那一层最 high quality 的，最下面的就是你一般路上所看到的影片之间有一个deformer， 有一个 deformer。要思考 deformer 这件事情，你其实应该从这里下去思考。大概知道我在说什么，给我一个0到1的数字。所以今天讲的东西跟之前讲的有一点点不一样，没有关系，但是我们需要偶尔出来穿插一下，有一些到底是什么的穿插一下哈。好，我们继续。所以这个 Okami 的这个案子这个论文可以下去看一下，就是把这个机器人如果可以转制的这件事情给描述到。那接下来其实加上强化学习或者 simulation 的环境，你的这个2只机器手背，或者是包括你的肩宽能够做到什么，其实是可以用强化学习在 simulation 的环境里面让它跑。你只要有机器让它跑，它是可以跑出它做任何动作之间，你给它打分数。它可以跑出来跟你的那个模拟是会很像的，很像你这个动作。那你不用真的人去打分数，你可以写你的比对，那个比对的 loss function 就变得很重要。强化学习其实在调整的有很多是那个 loss function 的原因。那我们还在做 imitation learning 的时候，我们动作的 quality 其实主要是来自于你对这个动作的理解，所以几乎会是卡在哪里？几乎会是卡在 video， 就是那个 data 所呈现出来的清晰，动作的清晰度 ，context 的清晰度，就是目前几乎是最重要的。那我们去往下看。然后这篇论文我为什么选出来的原因，也是因为如果你工厂里面的机器人，我说的是工厂里面的机器人，它不是这么需要人形的、这么泛化的这么多种工作，它所做的工作基本上就是几个。那其实这篇论文 你认得你那几个工作，然后它的 localization。如果你一般来讲的工厂环境会希望那个 localization 的就是入物件的摆放的位置要 exactly 落在什么地方。如果你要让它这个部分，我们说有 sorting machine， 然后有一些排序的特定工作机器人，那这种机器人如果在排序的工作上面没有办法让它做到停在同一个位置，停在同一个位置，非常稳定的停在同一个位置。以前的做法通常会用滚轮，然后接下来用各这样的 sorting machine 让它到你 camera 下面的时候，就是放的就是要一模一样的位置，那机器人去调动跟抓，然后慢慢的提供了一些弹性。那包括我自己做过的，包括那个饼干，就是饼干，它那个食品工厂，它巧克力啊，或者是那饼干做出来，它是用滚轮给滚出来的嘛，那你就要做一个抓取的手背，那抓取的手背是3轴的，下面是一个吸盘，它去抓东西，然后把它放到你的包装盒里面。你的包装盒里面大概就是一排，就是大概，比如说横的4个，然后直的10个，它就要很快的去抓东西，把它摆上去。所以那个演算法把它带过来。如果你是要做一些焊接的动作，它就比抓取还要更精准。那所以这个它移动的这个过程，把人的部分，现在影像上看到人的部分换成机器人就可以换掉。那中间所有的 AI， 这个论文当中中间所有的 AI 都可以拿来描述，就是你把这篇论文读完，大概就会知道那个东西怎么做。这边经常出现的这个 kinematics 就是动态的那个机械学，它钢体之间的关系，你把它倒回来算，所以叫 inverse。这个如果是人的话，已经有这种演算法了哈。
Of how we can demonstrate by manual backing and track the objects so that the robot can generate a reference plan. The robot can follow this plan and be deployed in diverse environments where you just saw. The nice thing about this is that now we can collect data without any teleoperating policy so that reactive RGB observation and the robots can text and also a robot with its camera and commands the low level.
你们还是可以看一下它的分数它的分数看起来是很好了，但是在实际上只有成功1半，只有成功80%，最多是把电脑盖上这个简单的动作，它也只成功了80%。这个，然后 close the door 就是把那个那个东西推进去，它也只成功75%。
So now saw like and then we show that as the robot can so we summary we allows the strong visual and spatial generation and also
这样的一篇论文，它其实有没有它的帮助？有，为什么？因为它是用 pipeline 组合起来，它是用好多个工作程序组合起来，意味着什么？意味着当你要学的时候，你会比较知道里面的细节是什么。那 VOA 有没有坏处？有，就是你到后面只要需要训练 data， 那你除非对 transformer 非常的熟悉，那你就是要一直去问 AI， 你有哪些 part 你可以换掉。那你去读这样的论文，其实可以得到更深的想法，不是说 work 的想法，但是你会知道有更多的技巧是怎么去解决问题的。好，这是前面我们先走过，因为我们自己公司昨天有一些讨论嘛，那我自己有一些想法，所以我就今天就稍微把这篇我看过的论文拿出来分享一下。那我们继续我们的旅程哈。
Here
我们稍微从前面一点点复习。
Pre-train on any robot action data, and we just fine-tune the base VLM. So this is basically for the sake of assessing whether it's important to pre-train on the robot data set. And of course, we have our full OpenVLA model, and this is the method that we mostly evaluate. Cool. And in terms of the setups, we tested on 2 real-world Franka Panda setups. Called Franka Tabletop and Franka Droid. The Franka Tabletop tasks include 3 narrow single instruction tasks. And basically, this is like a single skill task where it's not important to have language grounding. And then we also evaluate on 3 diverse multi-instruction tasks. So here you might have distractor objects and various language instructions. And basically, the model has to react and do the right thing given the user's prompts. And then the Franka droid task, it's a single instruction task. It's called Franka droid because we use the same hardware setup from the recently released droid dataset
应
paper.
该是比较无聊啊。
And this was another paper that made it into RSS 2024. Cool. So the narrow single instruction tasks look like this. You just have a simple setup, and you have to just do one skill. And we collect between like 50, or usually like around 50 demos for each task. And we also test against out of distribution variants of this task, like shown here. So you might use like a different object or unseen backgrounds as shown in the bottom. And a diverse multi-instruction. Oh yes, is there a
Seems
question?
like Marcos has a burning question.
Yes.
Hi
Marcos.
there. Yeah, just a quick one. Because in the beginning of the presentation, you mentioned just taking a third-person view image, and now I see this what looks like a RealSense dev
这个
camera
主理已
on
经
the
回答
picture.
过，就是它这只手背目前是没有放到 VOA 的训练里面哦。VOA 是用第三人的视角去做那个 data 的收集的。
Could you please explain what's the input here?
Yes, great question. So the input to all these policies is
我讲的是 Open VOA， 不是所有的 VOA。
just the third-person image that you're seeing here. The reason why there is an additional camera mounted on the robot's wrist is because this robot was used for a different project that used multiple inputs. But yeah, you can just ignore the camera on the robot's wrist. We're not taking any inputs from that camera for this project. But good clarification question. Cool. And moving on, so these are the diverse multi-instruction tasks. Here, there are multiple objects in the scene, and the user specifies which object to manipulate. And we have like basic pick and place tasks. We have knocking tasks, as well as tasks with a deformable object, such as a towel. And again, we have OOD variants of this task. So using different objects or distractor objects, or even like different object positions and orientations. And the final task is this wiping task. We want to show that we can do tasks that involve like different behaviors, such as wiping. So the task here is to grab the sweeper and sweep the food items into the dustpan. And again, we have an in distribution and an out of distribution variant of this task. Okay, jumping straight into the main experiments figure. So again, to parse the bar plots, we first have the diffusion policy variance in the blue and gray, and then there's Octo, OpenVLA trained from scratch, as well as a full OpenVLA. And what we found is that the diffusion policy variants actually perform best in the narrow single instruction tasks where language grounding is not important. And qualitatively, here are some videos to show this. So we have diffusion policy on the left, and it can do the task well. And in the middle and on the right, we have Octo and OpenVLA, respectively. And these are actually cherry-picked failures. Of course, these methods can do the task sometimes, but these are just examples of how it fails. On the other hand, we find that OpenVLA performs best in 4 out of the 7 tasks. And it does especially well in the diverse multi-instruction tasks where language grounding is important. So for example, here, we have 3 methods again, and we see that diffusion policy on the top left actually manipulates the wrong objects. On the bottom left, it actually fails to even touch any object. Octo in the middle gets pretty close. So it shows that it has good language grounding by going to the right object, but it doesn't fully finish the task. And then on the right, we see that OpenVLA is able to complete the task with the correct object. Breaking it down further, we also observe that Octo exhibits pretty strong language grounding as well, and it performs fairly well on 2 out of 3 of the diverse multi-instruction tasks. However, it struggles on the narrow single instruction tasks. And it may be that the fine-tuning dataset is too narrow for it to be fine-tuned on, and it may be overfitting to them more strongly than OpenVLA does. Overall, we see that OpenVLA performs the strongest and outperforms the next best baseline by 20% absolute success rate on average. And it's also the only method to get at least 50% success rate in all tasks. So we show that it's a good default to begin with if you want to start training on a new task. Lastly, the from scratch OpenVLA model without any sort of robot pre-training, that one seems to struggle overall, which shows that the robot pre-training is actually crucial if you want to achieve a good fine-tuning performance. And some qualitative examples we see here on the left that the from scratch baseline is unable to do the task reliably. Sometimes it even goes towards the wrong object that's shown on the bottom left. And then on the right, OpenVLA is able to complete these tasks more reliably. And this just shows that it's important. It's important that we have fine-tuned the model on the OpenX dataset. Cool, and you can check out our website for even more qualitative results. Is there another question?
我们会尽快走过 OpenBOA 哈，因为后面的那个
Yes, I got a question
跟
about
那
this
个
fine
会
tuning.
更
So
重
for
要，
the
所以我这边
data
会
set
比
collected,
较比
is
较
it,
不会
for
讲太
example, I
多。
saw you mentioned 50 to 60. Is there a sweet spot you think that, like, is there a, I'm wondering if there's a performance relationship, strong relationship with the numbers there. And also how different are those different episodes, like these objects in different locations?
Right, okay, that's a great question. So firstly, in terms of the number of episodes and its relation to performance, we actually didn't try like various like numbers of demonstrations for each task. We sort of just relied on intuition to just pick some number of demonstrations. And the idea was to just try to cover like the table, like the state space as much as possible. So we found that like 50 was like a good number for a lot of these tasks. You may have seen that for the diverse multi-instruction task, we needed more demonstrations, like 150, for example, for some of them. And this is just because there was like lots of different objects and lots of permutations of them. So we wanted to get enough coverage of the state space. However, like you actually don't need that many demonstrations if you are testing on like a narrower state space. So for example, for this flip pot upright task, like this third task in this row here, we actually only collected 10 demonstrations. And that's because the pot position was very, it had a very low variance, and it was just really in that small section of the table. So you can actually fine tune this large billion parameter model even on 10 demonstrations and get it to do the task. Yeah, and sorry, what was the second part of your question?
Oh yeah, and like how different are these different episodes for the data? Is it just objects in different locations?
Yes, great question. Yeah, so for the different episodes, so the different demonstrations, all the objects are like scrambled, so they're like moved in different locations. At evaluation time, it's that as well as different objects in the OOD generalization cases. So you might have like different distractor objects in the background, as well as like different target objects entirely. But mostly it's just like a shifting of the objects on the table.
Cool. Thanks for the questions there.
Awesome, thank you. Is there another question, or are we good?
We'll let you wrap up your talk, and we'll make questions on the chat alone, just so we can prioritize them, because there are more questions than are going to be able to be answered in the time that we have.
Awesome, sounds good. Okay, cool. Let me wrap up then. So we showed that OpenVLA can be fine-tuned effectively on new robot tasks, and I think unfortunately we won't be able to go into the additional experiments in much detail, but I'll give you the quick TLDR. Yeah, let me just jump through this.
One thing, Mujin, if you've got like 5 to 10 minutes to stay over for the questions, then maybe you can expand on this a little bit more right now. Would you be able to stay a little bit more for the questions after?
Yep, that sounds great.
Excellent, thank you.
Cool. Okay, then in that case, I'll go into some detail for these additional experiments. But basically the question we want to answer here is, do we actually need to fully fine-tune the model to get good performance? So in all the previous fine-tuning experiments, we actually fine-tuned all 7 billion parameter models. And yeah, surprisingly, it actually does quite well. With augmentations, it doesn't overfit and it's able to get reasonable performance. But maybe you don't have so much compute to actually do this full fine-tuning. And in that case, these parameter efficient fine-tuning methods may be more helpful. So we compared various fine-tuning strategies in our paper. And just to quickly go through them, this last layer only method fine-tunes only the last layer of the LLM backbone and freezes everything else. Frozen vision, in this method, we freeze the vision encoder, but then we unfreeze everything else. So we're still fine-tuning through the whole LLM backbone, just keeping the vision encoder frozen. Sandwich fine-tuning means that we fine-tune the vision encoder, so that's at the beginning of the network, as well as the last layer of the LLM, which is at the end of the network. And then everything else in between is frozen. And that's why we call it like a sandwich, it's like a frozen sandwich. And then the last parameter efficient fine-tuning method that we try is LoRa. And this is a popular low-rank adaptation method that is widely used in the LLM literature. And it's applied to all the linear layers of both the vision and language backbones. It may be hard to quickly understand all these, but I encourage you to check out the paper for more details. But basically, we compare these on a subset of the Franka tabletop tasks that we showed earlier. And we find that LoRa is actually the most effective. With a rank of 32, you're actually only training only 1.4% of the 7 billion parameters, but you can actually match the full fine-tuning performance shown in the top row. And you're doing this with like much lower VRAM utilization as well, which is great. On the other hand, we find that some of the other partial fine-tuning methods don't do so hot. For example, if you freeze the vision encoder, that typically is going to lead to poor performance. And this is even if you fine-tune the entire LLM backbone. So yeah, like even if you're training like almost 7 billion parameter models, if you're fine-tuning the wrong parts of the model, that can be mental. We find that the sandwich fine-tuning method, which only fine-tunes the vision encoder and the LLM last layer, this has a boost in performance compared to the frozen vision encoder methods, but it's still not as good as LoRa. But basically what this shows is that it's important to fine-tune the vision encoder. Okay, and so we talked about PEFT techniques for fine-tuning the model with lower compute. What if you don't care about fine-tuning at all and you just want to run the model? Do you need a large GPU to run these models? Actually, no, you don't. So you can use 4-bit quantization at test time to load and run the model with lower GPU memory. So normally what we do without
这个为什么用4bit 的那个 LoRa 就可以达到很好的效果？其实是因为它吐出的 token 主要是关节的角度，关节的角度它吐出来的时候，移动的角度啦，它只要方向对，它的 step 够快，它就可以做好。那它要避免的问题是它那个 jerk 的问题，就是它的最差，而且它不是要避免平均的，它是要避免最差的那一次的抖动。刚可以听懂了，给我一个0到1的数字。所以你在做这件事情的晶片，它不用很大，但是它要很快。我再说一次，所以这个晶片不用很大啊，它要很快。然后你刚刚看到它在调整的时候有分成用4种方法 ，freeze 它的 vision 的 encoder， 然后 freeze 它的 LLM 的，就只调整 vision， 只调整 LLM， 或者是2个 sandwich， 就是2个都调整。这个细节我们本来要讲，但是时间，因为我们在 OpenVIA 已经拖很久，我们后面用数学的角度再去大概的说明一下，然后我们希望明天就可以进到那个，我们今天可能就会停在，不管看到哪里就会先停在那边，然后我们明天会去看拍，那不是 OpenVIA 就不看了，我们会停下来往前走，然后再回来回溯，就是复习，然后说明里面的一些细节。那这个 4-bit 就能够达到一定效果，你从哲学跟逻辑上如果有概念的话，是预期得到的。LoRa 的效果最好也是预期得到的，有没有？你大概把我所讲的那个晶片为什么很重要的原理拿过来对应，大概有感觉的，给我一个0到1之间的数字。天下武功唯快不破，因为我们是从 Common Filter 带过来的，所以 Common Filter 里面就有讲了，你是预测跟侦测之间一直在做修正，所以只要修正的够快，修正之前其实就是方向要对，就这样子而已。好，我们再继续。
Quantization is that we cast OpenVLA to have precision, which is the B+16 data type at test time, and this requires around 16 gigabytes of GPU memory. But if you use int for quantization, basically you only need 7 gigabytes of VRAM to run OpenVLA, and this is nice because a lot of non-server grade GPUs have sufficient memory for this. And what's also nice is that we didn't actually observe any performance degradation in our evaluation. And this was on a subset of bridge data tasks, not on the full evaluation suite. So things may differ if we had evaluated on more, but at least on the subset of tasks, we didn't observe any sort of performance degradation, which was surprising. Another slightly surprising finding is that the 8-bit quantization actually didn't perform as well. And this is potentially due to just like different implementations of the quantization between int 8 and int 4. But this implementation of the 8-bit quantization led to lower inference speed, and this may have messed up the dynamics at test time, and that may have been a confounding factor in our evaluation. But basically, we find that 4-bit quantization at inference time worked pretty well. Okay, let me just quickly fast forward through.
那这边他在讲说，为什么8-bit 会反应的比较差，并不是8-bit 精度的问题，而是它的那个 low inference 的 speed 速度比较重要，速度是比较重要。甚至如果照这个原理来讲，你可能甚至不需要做到 4-bit， 你还可以把它再压得更低，搞不好效果会更好。不一定啊，可能 4-bit 就是一个 sweet spot。但是我们用语言模型大部分都是用 4-bit， 对不对？那你语言模型的如果低于 4-bit， 它有可能就会 那个相位空间会破坏，所以要找到那个甜蜜点，就是你的相位空间的甜蜜点，然后跟速度这件事情的甜蜜点。那在 4bit 我们一般的语言模型，其实现在聪明的把它用多了，讲到 4bit， 这个是大家业界已经是可以认同的。8bit 很 OK 很棒，但是因为速度不够快，所以如果你有一个晶片可以跑得很快，那其实你用8bit， 我相信一定会比 4bit 更好。这样子，就是它是一个两者的参数之间的关系。
At test time, and that may have been a confounding factor in our evaluation. But basically, we find that 4 bits quantization at inference time worked pretty well. Okay, let me just quickly fast forward through these last few slides. But basically, there's a few design decisions that we made and some insights that we've gained from this project. First, which vision language model to fine tune? So obviously, there's lots of VLMs out there. How do we decide on the prismatic VLM? So we actually tried 3 different ones: the IDFix V1 model, Lava V1.5, and the prismatic VLM. And we found that Lava outperformed IDFix by quite a significant amount, like 35% in absolute success rates. But then like moving on to prismatic VLMs, the performance increase started to diminish a little bit, even though the underlying VLM was much better. If you use a better VLM, then probably the performance of OpenVLA would be better as well. In terms of image resolution, we tried both 224 by 224 and 384 by 384 pixels. And for us, we observed no difference in the performance in our bridge evaluations. However, the 384 pixel resolution just took 3 times longer to train because you have many more patches and many more tokens to train on. So we just opted for the smaller image resolution. This question about whether to freeze or fine-tune the vision encoder was an important question for us because prior work on vision language models found that freezing the vision encoder led to much better performance because you don't disturb the pre-trained visual representations. However, for us, we actually found the opposite, and basically fine-tuning was crucial for both the zero-shot experiments and the fine-tuning experiments. And our intuition here is that perhaps the pre-trained vision representations aren't sufficient for robotic control yet because maybe they haven't been fine-tuned for robotic control tasks. Oh, sorry, I meant they haven't been pre-trained on the robotic control tasks. And how long to train these models? We actually consistently found that just training for longer was better. For example, we went through 30 epochs of the OpenX mixture that we described. This is in contrast to prior VLM works that may go through like 1 or 2 epochs only. Which learning rates? We did a hyperparameter sweep, and we actually found that using the same learning rates used in the VLM pre-training phase led to the best results. And by best results, I mean it learned fastest and still maintained good performance. And the nice thing is that we kept it very simple and we just used a constant learning rate. So no need to do linear decay. Despite doing this, we still observed strong performance. It's possible that you could optimize this further with different learning rate schedules and get even better performance, but we found that it was not necessary for our evaluations. Cool. In terms of limitations, so OpenVLA it's a strong model. It's currently the state-of-the-art generalist model, but there are several limitations. First, it only supports single frame inputs and single step actions. And the reason is like this is a large model with billions of parameters. And on a local GPU, the training and inference speed is very low. If you have even more inputs and outputs, the speed would be even lower, which would not be great when you're trying to deploy these models on real hardware. So the question here would be, how would the performance change if we did have these additional inputs and somehow like sped up the model so that it didn't, it would be able to run on local GPUs on real hardware. Another limitation is that there's lack of support for high frequency controllers and bimanual manipulation robots because we pre-trained mostly on single arm robot data sets. For example, you can't deploy OpenVLA on Aloha or other bimanual manipulators out of the box. Fine-tuning is a different question though, and that could be a nice future work. The reason here is, as I mentioned, it's hard to run these models at high frequency. Even when we're using remote H100 servers, at best we could only run the model at like 7 to 9 hertz. For local GPUs, we got it to run at like 3 hertz best. So it'll be interesting to see if VLM inference speedup tricks that are like well known in the literature can also enable high frequency control for VLA models. So that could be a nice future work. Another limitation is that the VLM, the pre-trained VLM is only fine-tuned on robot action data, as I mentioned earlier. So we're not fine-tuning on both robot and VQA data.
这边里面有提到一些关键字，你可以自己查一下，像 VQA 是什么？ fine tune on robot data 就是什么？这里面的关键字其实你可以自己稍微问一下哦，这样子。
And as I mentioned earlier, this may lead to some sort of catastrophic
比
forgetting.
如说这边的这个灾难性的遗忘哦，灾难性的遗忘，这个是我们在语言模型空间里面，就是你的 latent 空间里面整个能量已经错置了，就空间里面的能量已经有很明显的聚集或者是很明显的破坏哦，这个相位空间被破坏就是这个灾难性遗忘的原因。那 doesn't appear in robot interaction， 对，这个在 robot 里面为什么没有出现的原因，其实比较简单，因为它有把动作切成一块一块去修正，所以这个灾难性的遗忘比较不会出现。
Of the pre-training concepts that don't appear in the robot interaction data. And if we had more compute, it would be a good question to explore and like whether co-fine tuning can be used to improve generalization performance and prevent catastrophic forgetting. So there's lots of questions that come up from these limitations, and we hope that the other researchers can build off of OpenVLA to answer some of these questions. Okay, I'm super thankful for my amazing collaborators listed here. It was a pleasure to work with everyone on this
但
team.
后面的 Q&A 比较有趣嘛，所以我们还是把它看完。我们今天大概就是把它这篇影片里面尽可能的看完这样子。
And also thank you all for listening. And
For the questions, this is a record number of questions by far for any of the robot paper discussion. So nice one, Mujin. So I'm gonna like clear the slate for questions here. We'll take questions only in the message box if that's okay. Put an asterisk in front of your question if you want to unmute. Otherwise, I'm just going to read your question for you, and I'm going to try to prioritize them by how specific they are to this talk, the variety they introduce to the questions, and I'll try to give everyone a turn. So anyone who's already asked the question, I'll deprioritize just a little bit. Okay, so I've got one question up right now from Vitali. Is it possible to use smaller LLMs for the backbone? Like, can you use a model like Phi 3 Mini? And do you think it would perform at the same level as Llama 2 given enough training?
That's a great question. Can you use a smaller LLM? You certainly can. The only difficulty here would be that you would have to either do all the pre-training again or try to distill this model into that smaller model. But yeah, I think this is a great like open question. And I think as long as the underlying like vision language model has good spatial awareness and good object detection, I think it would be sufficient for VLA fine-tuning. Yeah, so I think like as you improve the base VLM, performance will increase. However, if the base VLM has like sufficient understanding of like physical scenes, then it should be good enough. But yeah, I think it is a good question and something that is worth exploring.
All right, and let's actually piggyback on that question and go the opposite direction. Someone says, Barbunya says, what about, are you thinking about using bigger backbones like Llama 3 405 billion? Do we have enough data to effectively leverage these?
That's a great question. So Llama 3.1 was just released yesterday, and they have like 400 billion parameter model. For us, due to being based in academia, we probably won't be fine-tuning a model that large. But in theory, like it should be able to be used for VLA pre-training. But yeah, it will just take a long time to train because it's another order of magnitude larger than the current OpenVLA model. So to provide some insights for the training of OpenVLA, it's a 7 billion parameter model, and we used 64 A100s for 14 weeks to train the model. And this was
你有讲到那个数字哈，用了大概的多少的电脑？单单是这个比较小的 Llama 2的模型，他们用了多少
be used for VLA pre-training. But yeah, it will just take a long time to train because it's another order of magnitude larger than the current OpenVLA model. So to provide some insights for the training of OpenVLA, it's a 7 billion parameter model, and we used 64 A100s.
64个用64个那个 A1 的显卡
for 14 weeks to train the model.
然后花了14个月，14个月除以4，大概就是3个多月，14个礼拜啦，3个多月。
And this was thanks to Toyota Research who provided the compute, but you would have to use a lot more compute to train a model that large. But I would expect it to work as well, provided that you have sufficient amounts of robot data.
Julian also, this is another question, but he said Llama 3 with 405 billion parameters is the Terminator. So I find that pretty funny. So I'm going to chain two questions together here. There's one from, and they're both about next steps. So Namra says, now that we have state-of-the-art open source VLA model, but we're still not that great at out-of-distribution tasks and long horizon tasks, what research questions do you really want to see answered in the next year? And just 1 second, because Simon also asks, what are the next steps following your work, and what component would you say, I mean, what's the next low-hanging fruit for improving success rates?
Great. Let me answer the second question first. In terms of the low-hanging fruits, I mentioned like several limitations in terms of the current model, which is that we have like basically like a single step policy where we take a single step as input and predict a single action as outputs. And as you saw, the full diffusion policy baseline in the fine-tuning experiments had various bells and whistles that improved its performance. So we would expect those sort of things to also improve OpenVLA. Another thing that I didn't touch upon too much was one of the baselines, Octo, uses diffusion to regress to continuous valued actions. And generally, like diffusion is a very expressive method that can learn pretty multimodal policies. And yeah, it would be like a nice thing to figure out whether VLA models can be adapted with diffusion to perform even better, or whether these autoregressive next token prediction models are still more powerful. So that's still an open question, and we don't know for sure. So those are some low-hanging fruit that people can look into. Could you remind me the first question, Alex?
The first question from Namra was, I'll just read it verbatim. Now that we have state-of-the-art open source VLA model, but we are still not great at out-of-distribution tasks and long horizon tasks, what research questions do you really want to see answered in the next year? So maybe you've answered part of that, but let me know if you think that you want to add more.
Right. So in terms of the generalization abilities, I think one research question is like, how important is the co-fine-tuning exactly? I had mentioned that co-fine-tuning on robot action data and internet pre-training data may have enabled RT2X to do better semantic generalization. However, it's not super clear because the VQA pre-training data set is really just like visual question answering on like static images, and it's not really clear like how much transfers. So one nice question that's still open is like how do we get things to like transfer better to robotic control, and like how important is this co-fine tuning exactly, and like how much does it improve generalization? In terms of long horizon tasks, yes, it would be nice if these VLA models were fine-tuned and adapted to long horizon / bimanual / dexterous tasks. Most of the skills that we trained on were more short horizon, and you can think of VLA as like a low-level, like a large low-level controller that can do various short horizon tasks. It's possible that you can chain these skills together to do long horizon tasks, but yeah, it would be cool if someone took a VLA model and then fine-tuned it on like long horizon like skills, for example, that require like lots and lots of steps, and did more advanced behaviors than what we've seen in this project. But I think those are some nice longer term research questions to explore.
Thank you. So two quick questions in succession that are kind of related. So Marcos asks, so if you see a failure mode when you've trained VLA, open VLA model for a task, if you see a failure mode, if you then just take those episodes where, or take those setups where you saw the failure mode and try to fine tune on those, will you be able to address the failure mode?
Yeah, that's a good question. So it's like, if the model fails in a certain way, can you sort of correct it? Yeah, I think if you do some sort of like Dagger style approach where you collect demonstrations in cases where the model fails specifically, eventually it should be able to improve. The drawback is that you have to really investigate like where it fails and then have a human in the loop to collect more data on top of all the data that it's already fine-tuned on, and then do another round of fine-tuning. But in theory, it should work. It's just like another, at the end of the day, this is just another imitation learning policy. So anything that you do to improve other imitation learning policies should also work here.
And maybe somewhat related, Vitaly asks, if you've looked at scaling laws of the amount of fine-tuning data, so his question verbatim, how much does the success rate drop if given half the samples to fine-tune? And have you been able to see where it plateaus based on the amount of data provided?
Yeah, that's an excellent question. For this project, in terms of scaling laws, we haven't been able to do like extensive analysis just because we were pretty limited on compute. However, we have done some ablations where we like ablate the OpenX pre-training. So for example, for the bridge evaluations, we have tried just training VLA models on bridge only versus bridge plus all the other data sets in the OpenX mixture. And we did find that the additional raw data did improve performance substantially. However, yeah, we don't have like very fine-grained analysis for this, unfortunately. So like how much the performance differs if you cut the training data by half. That's an excellent question, but unfortunately we don't know the answer there. But we do find that generally like more OpenX pre-training led to better performance.
Thank you. So Remy and Matt are asking, are deltas? So you said the way that you look at the tasks, the XYZ components like delta X, delta Y, delta Z. So are these deltas in the group frame or the world frame?
That's a good question. So the delta XYZs, and let me try to pull up the reports about that. Yeah, so these deltas, these are in the robot's base frame. So they're not in the gripper frame. So yeah, if the robot was oriented differently, that changes things. But a lot of the data sets, they have the robot oriented in this sort of top-down manner. There are some data sets where that's not the case, and we don't really do any sort of like manual alignment of the data sets. We really just let the model learn what it needs to figure out the alignment on its own. The alignment in terms of like the coordinate frame and like what action it should output. But yes, these are in the robot's base.
Xavier, would you like to unmute for your question?
Yes. Another question about the done signal. So I see that OpenVLA is not trained on the done signal. Then how does the model know when a task is done?
Oh, okay. Good question. So yes, we don't train unless the data set. Actually no, we don't train on like a done signal. So really the model at deployment time, it doesn't know when it's done, and you have to like manually stop it, or the timer on the episode runs out. So for example, for the bridge evaluations, you might have like 50 time steps, which is like 10 seconds. And then the model either like does the task or not in that time frame. However, actually some data sets, they may not have like an explicit done signal, but the expert demonstrator may have stopped moving the robot at the end of the episode. So for bridge evaluations, we often found that OpenVLA, after doing a task, it would just like stay still, but it wouldn't terminate itself. But that's a good question.
Great.
Yeah. But one thing to note is that you can add that to the action space if you wanted to. It's just we haven't done that because it's not a universal thing across all these different data sets. But great question.
Yeah, thanks.
Olivier asks who checked the Llama 7 billion or the backbone's performance on NLP tasks after fine-tuning it. So how much of its prior did it retain?
Okay, that's a good question. So after fine-tuning it, we actually don't expect it to work on the other like LLM or VLM pre-training task anymore. And this is because we are doing this full fine-tuning of the model, and it's only trained to predict these robot action tokens, which is in a very like limited subset of the model's vocabulary. So if you try to chat with this model, it's not going to work because it's not fine-tuned to do that. So really, the OpenVLA model is just for robotic control. However, if you wanted to, you could use other fine-tuning methods, such as, for example, you could do like, I guess in theory, you could try to do LoRa fine-tuning for the pre-training phase. So like we fully fine-tune the model for OpenX pre-training, but what if you use LoRa, or if you use like adapter layers to keep the pre-training weights frozen and just modify a smaller subset of weights. In theory, that could be used to
这里面
cover
讲到的
performance
这
on
个
the pre-training.
fine-tuning 的技巧还蛮多的，那跟知识真的也有一点点像，所以如果没有看懂的没有关系哦，就是大概他跟你讲说，他 fine-tune 这个东西的过程是根据这个也简报，它出来的就是各个状态，它预测状态之间的 delta 就是那个 change， 所以它并不是用来对话的，但是如果你要把它做成对话的也可以，用成对话的就是将来有可能就一边在做的时候，我会说好，我这个动作接下来要干嘛，接下来要干嘛，他给他 reason， 但是这样子其实短期之间是不会发生的，因为我们现在连动作都还做不好，你要解释动作这件事情啊，是你动作做好之后，大家才会对黑盒子里面的发生的那个 intention 意图去做分析哈。好，因为时间的关系，我们今天就是先到这里，我们明天会跳到拍去哈，明天就会跳到拍去了，所以我们这个 OpenVLA 并不是这样就看完了，我们只是先带过一遍，因为我们会用之前那一位之前的这一位我们不是从 VLA， 我们是从 VLA， 我们会从他那个我们会用这一位的这一位我们会用那个要怎么念
do some extra training。
我们会用它的整个系列下来做影片的整理因为他尝试过很多个 VLA， 所以跟着他你比较能够把整体的概念搞清楚所以目标是先各个击破，然后再回来他的影片做整合。好，以上是今天的内容，希望是对你有帮助的。先给我2个分数，那我们今天就到这边，谢谢。